Good evening, everyone. My name is Aditya Sharma, and this is Power Plant System Engineering course being conducted under the NPTEL program by Department of Mechanical Engineering, IIT Guwahati. Instructor for this course is Professor Niranjan Sahu from Department of Mechanical Engineering, and I'm your teaching assistant, TA, for this tutorial or for these series of tutorials. So till now we have taken 9 such tutorials corresponding to each week of this particular course. And as we are into the 10th week of this course, so corresponding to that, we are conducting tutorial 10. And the broad topic of this week's content is hydro and renewable energy power generation system. I believe the next week's content also comes under this broad topic only. So we shall first see the hydroelectric power plants, and then we'll discuss wind energy. So total 4 lectures are there. All right. And yes, let's wait for a couple of minutes. After that, we will start today's session. Okay, so we can then start with today's session. So contents of the slide are this way. So total four lectures are there. Okay, so we shall see first topic, then questions for a particular lecture, and the same way we shall move forward in our session. Right. So first we have hydropower system, then we again have hydropower system, then we have wind energy, then again we have wind energy. So let's start with hydropower system part one. So these are the topics of lecture number 25, hydropower system part one. So we have topics like hydroelectric power plant, water power, what are its advantages and disadvantages of this power plant, and what are the elements of a hydroelectric power plant. Right. Then are the turbines used in this power plant to convert your energy that is there in water first in the form of potential energy, and then that is converted to kinetic energy, and this kinetic energy is converted to the shaft work, right? And that shaft work is then converted to electricity. So from kinetic energy of water to shaft work is converted using our hydraulic turbines. Then is Pelton. So Pelton wheel. So Pelton turbine then is discussed. Its velocity diagram, then deflection angle and velocity diagram. This have been discussed. Then energy transfer in Pelton turbine. Then what is the optimum velocity of bucket? Then what is hydraulic efficiency? Hydraulic efficiency basically is the power that you produce. It is the ratio of the power that you produce to electric energy. Sorry, it's the power that is imparted to the turbine, right? The useful energy, and divided by the energy, the kinetic energy that you are giving to your turbine. So that efficiency. Yes. So this basically is the ratio of energy transfer by kinetic energy that you give, or the total energy that you give. Okay, of water. In case of Pelton turbine, because later we will see the concept of degree of reaction. This is the same degree of reaction that we have seen in the previous lectures on turbines in case of your vapor power systems. Then maximum hydraulic efficiency has been calculated, and then discharge and velocity of wheel, how can we calculate? So all this has been discussed. So briefly, we shall see one by one these topics. So first is your hydro power plant, right? So first topic is in it is water power. So this I have told that potential energy water has, right? And this is channelized to a turbine through some channel that we sometimes call conduit, right? Or penstock. So that is your water power. Technologies have been mentioned. So what are the advantages? So its running cost is low, right? And its expectancy is very high, right? And the dams that you build to harness the water power, so they can be used to control your floods, right? In case there is heavy downpour in your catchment area, so the area downstream of your dam, so that it doesn't get flooded. So this can be used. Dam can be used to avoid that. Yes. And then for irrigation, also dams are used. The reservoir that you get from your dam. So water from there can be used for irrigation. This. And then disadvantages. So first, its gestation period is very high. Okay. Somewhere. So this whole process is very lengthy process. It takes years for establishing one such dam. Okay. In that case, the capital cost is high. And then where your dam is and where your end user is, the distance between these two is very large. In that case, large transmission lines to carry the electricity have to be used. And larger the length of the transmission lines, larger will be the losses, transmission losses. Okay. Then are elements of hydroelectric power plant. So what are the elements? Catchment area. What is the catchment area? So catchment area is that whole area from where your, so let's say we are building a dam on a river, right? In that case, the whole um area upstream of that dam, right? From where your water is getting collected into that river. Okay, so that area is your catchment area. Then is your reservoir. Reservoir is the water body that you get upstream of your dam when you have installed a dam. Okay. Then conduit. Conduit is used to channelize your water towards your turbine. Okay, from some height. So let's say we have at this height we have water, so it has to be channelized. So it will be channelized this way. Okay, here we will have turbine, then exit. This will be connected to generators. This is your turbine. This is your dam. This is your conduit. Okay. So these major elements of a hydroelectric power plant are. Then next topic is your hydraulic turbines. So turbines we have discussed in vapor power system. The same way we have turbines here. Okay. There the turbines were being run using your vapor. The vapor was being expanded in your turbines. Here you use turbines to get shaft work. So there are turbines like your Pelton turbine, turbines like your Francis turbine, right? Turbine like your Kaplan turbine, right? So these types of turbines are there, and how they are different from one another, we shall see. So based on discharge, if the discharge of water is low, you use Pelton turbine. If it increases, further increases, we use Francis turbine. And if the discharge is too high, in that case, Kaplan turbine is used. Okay. Then there are modes. One is impulse mode, then is reaction mode. What is an impulse mode? Impulse mode basically is when your water coming from your dam through conduit, right? So before entering the turbine, what we do, we use a nozzle, okay, to again speed up the water to increase its velocity. And if you see the entry and exit of the turbine, in that case, the major contribution to the shaft work or the energy transfer from water is from the kinetic energy of water. And across the turbine, there is no pressure drop. Okay. So the shaft work is through kinetic energy and not kinetic energy conversion and not the pressure drop. So this is basically impulse. And in reaction is when the pressure drop is causing the shaft work across the turbine. Okay, so that is your basically the reaction mode or reaction mode. Then is your directions. So direction of flow. So let's say this is something like this. This is your turbine, right? So this will move in this direction. So blades here, the blades will be here. Okay. Then if The flow is in this direction, right, along the axis. In that case, this is axial flow, right? If it is, let's say, from here, if water is entering and it is perpendicular to this shaft, in that case, it will be radial, right? And in that, if the water is tangential to this circumference, okay, tangential this way, in that case, it will be tangential flow, right? So the visualization in 2D is a bit limited, but I hope radial, axial, and tangential. And based on the way flow enters and exits the turbine, we define different types of turbines. Okay. So if the flow is tangential, in that case we call it as Pelton turbine. If the flow is axial, in that case it is Kaplan turbine or propeller turbine. And if your entry in the turbine of water is radial, in that case that is Francis turbine. Okay. And in Francis turbine, the exit is your axial and your entry is radial. Okay. So these are the major types of turbines used in your hydroelectric power plants. Then Pelton turbine has been discussed. Okay, if you see the topics, Pelton turbine has been discussed. So about 7 subheadings are there in this topic. So you see Pelton turbine. First of all, it's an impulse turbine, right? So this is for used for high head installations. High head installations. Now, what is head? Head basically is the height up to which the water uh, has been kept upstream of your dam. Okay, so the maximum height that is available to us of water, of the dammed water. Okay, so that is basically your head. So Pelton turbines are used when high head installations are used, right? Then velocity diagram. Important topic is velocity diagram. If you understand velocity diagram, you will be able to understand the function. Okay. So its blade is something like this. So this is the cross section of the blade. Okay, that is mounted on your shaft. So this is your cross section area of Pelton turbine. Then velocity, absolute velocity, velocity enters this way, right? Exits in this direction. This is the relative velocity VR2. This is VB is the blade velocity. Okay. Then if you join this with this, if you draw tangent, right? If you draw tangent here and then take this angle, this is your deflection angle. Now you draw the velocity diagram. So this is your velocity diagram. This is VR2. This is VB, and this is W subscript is your work velocity, which is tangential velocity. R is for your, sorry, this is your, this basically is your PW2. Okay, and this is your V2. So W subscript is work velocity, that is tangential velocity. Then B is your blade velocity. R is your relative velocity. Okay, so this is your velocity diagram for your blade or bucket for your Pelton turbine, right? Blade of a Pelton turbine. I hope you understand this cross section. Okay, so this is the, from upside, if you see the blade, that is this. So this is your shaft. The cross section is here. Okay, and this cross section moves. It has a depth or height or length, whatever you call it, up to the shaft, right? And this is shaft. So on the circumference of this, along the circumference of this shaft, you will have blades, like blades like this, like this. Okay, and this is the tip. In that case, this is the cross section that they are showing to us. All right, then expression for your energy transfer is given, right? I'll not jot that down. So expression for energy transfer, then optimum velocity of bucket, of blade velocity. So if you are giving velocity v1, in that case optimum velocity is v1 by 2. Okay, right. Same way, then we have expressions for discharge and the velocity of v. So expressions you can go through the lectures video, right? So briefly I have discussed the topics. Now we shall see questions. So first question is there, which says that the entire area behind the dam draining into a stream or river across which the dam is constructed is called as what? So this is spillway, surge tank, catchment area, or powerhouse. So this area is your catchment area. I have mentioned it, okay, in the topics discussion. So C is the correct answer to this question. Then we will see the next question. So yes, read the question, what it says, and there are four options. So elements of a hydroelectric power plant have been given. Out of these elements, the excess water is relieved through which element? So the excess water in a dam is relieved through spillway. The element to which it is done is called as spillway, right? It's not draft tube, it's not surge tank, it's not air conduit, it's spillway. So option A is correct. So a channel that leads water to turbine is known as a conduit. D option. Okay, so these are questions on the elements of your hydropower plant. So this is a true or false type of question. Question number 4, which says that in a reaction turbine only kinetic energy of the water and no pressure drop is used to obtain shaft work. Whether this is a correct statement or not. So we have two types of turbines based on the way they convert the energy in water to shaft work. In your impulse turbine, kinetic energy is used, and in your reaction turbine, both kinetic energy and pressure drop are used. Question here says that only kinetic energy of water is used to obtain shaft work, which is false. Both pressure drop and kinetic energy of water are used. Moving on to next question. So four options have been given. Question number five, it says that in which of the following turbines the direction of water is axial with respect to the wheel or shaft. So whether this is Pelton, Francis, Kepler, or Darius. Also, I strongly suggest that you please go through animations that are easily available on YouTube of the flow of water in different types of turbines. It is very important to visualize the way water is flowing in a particular turbine. So, whenever you find times, please go through such animations on YouTube that will enhance your learning. So, axial flow is seen as so in your Pelton you see tangential, in your Francis you see radial, and later axial. This is mixed. Here this is diagonal. Okay. This is neither parallel nor perpendicular. Nor perpendicular to your axis. Okay, that is your Darius turbine. So the correct option is C. Okay, so this was your question number fifth. Then is your question number six. It says that in a Pelton turbine, optimum bucket velocity is the product of absolute velocity of water and dash. Optimum bucket velocity VB. Sorry. So this is your optimum bucket velocity VB. Its the relation with V1. You have to tell V1 into dash. Four options have been given. Is it one half, third of one, one third, or two third? So for your Pelton, first of all, you have question number six. You have energy transfer is given by this. Theta is your deflection angle. V1, VB, we know what is. Then G is acceleration due to gravity. And K is your VR2 by VR1. Okay. R is your relative velocity. This is called blade friction coefficient. Then to find your optimum velocity, we differentiate it with VB. And doing that, what we get from here, we get VB equals to V1 by 2. Now let's answer this question. So VB is V1 by 2. So this will be half. In that case, the correct answer is your B. So this was question number 6. So this was it about lecture number 25. Then lecture number 26. Let's see the topics. Hydroelectric power plant, water power, degree of reaction. So degree of reaction, we know energy transfer from pressure drop. But total energy transfer. Okay, this is your degree of reaction. Total includes kinetic and because of velocity and your pressure drop. Then is Francis turbine. To visualize Francis turbine, you see some animation on YouTube. Highly recommended. Then velocity triangle. So I'll draw that. Then propeller and Kaplan turbine. And what is specific speed for hydraulic turbines? That what is scale ratio, unit speed, unit power, unit. So unit speed, unit power, unit discharge corresponds to H equals to 1 meter. What is H? H is your head. I hope head you remember the height of water in the reservoir. Okay, at your dam. So unit, all the unit terms correspond to that. Then let's see the topics. So hydroelectric power plant. This is basic from previous lecture. And what is your water power? We know. Then is important is your degree of reaction. So important is your degree of reaction. Yes. So degree of reaction I have, I believe, already written here. Okay. Then is Francis turbine. So what is your Francis turbine? It has mixed flow first of all. Okay. Radial inlet, axial outlet. Then the velocity diagram. Velocity diagram I'll draw. So this is cross section of the blade in your Francis turbine. So this is VB1 blade velocity. This is V1 absolute velocity. This is your relative velocity. If you have some doubt on these, you can just comment it down. I'll be Happy to answer. Okay, this. It's your VB1. So VF is your flow velocity. Okay. So let's say this is your shaft where your blades are mounted this in this direction, in this direction, in this direction, perpendicular to this way. Okay, right? Then the axial direction in which the flow, yes, right? Yes. So along the shaft, the component of water that is along the shaft, that is your basically flow velocity. Okay. So this is your velocity diagram for your Francis turbine. Then for your Kaplan propeller turbine. In it, the flow is in axial direction. Okay, so its velocity diagram is this way. The subscripts bear the same meaning. R is for relative, just number if it has been given. It is absolute. Okay, yes. So this is your velocity diagram for your Kaplan and your propeller turbine. Okay. Then what is your specific speed? So specific speed basically is your RPM. Okay. Then power generated by the turbine, root of that. Then your head raised power 5 by 4. So this is basically your specific speed for hydraulic turbines. So what has been done? Your RPM has been related to your power first of all, and then your head. Okay. So this way we can compare different turbines based on the specific speed. Okay. Then scale ratio has been also discussed, which basically is the ratio of diameter of your model turbine to its prototype. Basically, all these discussions are for the comparison. So if we have to compare different turbines, so how do we compare different turbines? Okay. So this is discussion on lecture number 26. Then questions. So we are at 13. Okay. So question number 7, it says that the degree of reaction for a hydraulic turbine is defined as the ratio of energy transfer due to kinetic energy to the total energy transfer. So whether this is true or false. So this is the ratio of energy transfer due to pressure drop, not kinetic energy. So this is a false statement. Question number 7. I hope there is no doubt in it. Then next question is, which of the following is an impulse turbine and what is the degree of reaction of it? You have to find impulse turbine and degree of reaction. So we know the degree of reaction of impulse turbine is 0 because here from pressure drop there is no energy transfer. Okay. So two options are there, Pelton and Kaplan. So out of Kaplan and Pelton, we know only Pelton is your impulse turbine. Okay. So A option is correct. Then next question. Question number 9. It says that in a Francis turbine, direction of the flow is dash at the inlet and dash at the outlet. So I have discussed this. The direction of the flow is radial at the beginning and then axial at the outlet. So if you see the options, B option is correct. Okay. So 1 hour already has passed since we have started this session. So we'll take a short break and then after that we shall resume with the remaining session. Thank you. Let's continue with the session. So on specific speed of turbine is the speed of operation of a geometrically similar model turbine produces this and operating under a head of 1 meter. So head is 1 meter. When the head is 1 meter and the power produced is 1 kilowatt, in that case, if we have two different turbines that are geometrically similar, in that case, the speed of operation of these two turbines can be compared. But this is basically the single, this talks about single turbine, right? So specific turbine, yes. So this is about a model of your turbine, right? Where the produced power is this and the head is 1 meter. And this turbine is geometrically similar to your real turbine, right? In that case, the operating speed of this turbine, that operating speed is your specific speed. Okay, so this is a correct statement. Option A. Question number 10. Then we have next numericals. In a hydropower station, water is available at this rate. Sorry. And head is given as this. So the turbine should run at this. And its efficiency is this. Then use the density of water as this and the acceleration due to gravity is this. And based on this information, we need to find out if the Francis turbines are employed with maximum specific speed. So specific speed of the Francis turbines to be used is given. In that case, how many turbines can be applied. Okay. So first of all, so for your question number 11 and 12. So discharge is given as 178 meter cube per second. Then head is given as 16.5 meter. Then RPM is given as 52. This efficiency is given as this. Density is given as this. And acceleration due to gravity is given as this. Okay. Based on the discharge and head and efficiency and density and this, we can find out the total power developed. This is rho GH Q efficiency. Okay. And when we convert it into, so this is watts. When we convert it into kilowatts, we multiply by 10 raised to the minus 3. Okay. 1000 into 9.8 into 16.5. 178 into 0.836. When we calculate this, this comes out to be 24062.25 kilowatts. Please check if the calculation is correct. Okay. Then, so here write as 451. Okay. Then specific speed is 451. And NS is N P root H 5 by 4. So in that case, from one turbine, how much pressure we can get? Square. Now if we place the values, RPM is this square. So this will be 9735.89 kilowatts. Okay. So number of turbines, if you see, is E divided by 9735.89. So this comes out to be 2.47. So this is a fraction. Your turbine cannot be in fraction. So either it will be 2 or it will be 3, right? So if we place 3 turbines, in that case the power produced will exceed this value, right? I believe that should not happen. In that case, 2 turbines should be the correct answer. Okay. Then question number 12 solution. And if you have to develop this much power, then you'll have to have 3 turbines. In that case, the power developed will be more than this. Okay. All right. Then is for your Kaplan turbine, specific speed is given. NS is 361. So P is your NSH 5 by 4 divided by N square. I have not changed it. 361 right here. So this will be 361 into 16.5, 152 square. So this comes out to be this much kilowatts. Okay. Then number of turbines. Yes. P by 6237.88. So if you find this out, this will be 3.85. So this is less than 4. So now turbines cannot be in fraction. So based on discharge, if we take 4, that will exceed the power developed based on discharge. And if we keep 3 turbines, so it will be within that discharge limit. Okay, so this was question number 12. So I have kept the answer within the discharge based on the power developed, keeping the discharge. Okay, and I've kept it within that limit. So this was it about your lecture number 26. Now 2 lectures are left. So topics are renewable energy resources, wind energy potential, principle of wind power, then forces on wind turbines blades. Renewable energy resources. We know renewable energy resources that can be renewed. Fossil fuel, petrol, diesel, coal, all are non-renewable. Wind energy, solar energy, geothermal energy, tidal energy. These are sources of renewable energies. Okay. So in the renewable energy resources, wind energy will be discussed in next 2 lectures, or has been discussed. So the concept of wind. So wind has been broadly categorized into planetary and local. So planetary wind is, so the concept of wind is the heat differences in the air lead to this circulation. Okay. The cold air is heavier, so it sinks. Warm air is lighter, so it lifts. So cold will come down and sink, and the hot air will lift, and this gives rise to your whole circulation, and which we see in the form of wind. So planetary winds are, because if you see your equatorial region, the heat received in the equatorial regions compared to the poles is high. So this gives to planetary winds. Okay. Then is your local winds. So local winds basically is your planetary is because of your equator and poles differential heating. Okay. Local winds is because of differential heating of land and water. Differential heating of hills compared to plains. Okay, so this is local winds. So concept is same. Cold air will sink and the warm air will lift. Okay, so this is local winds. Then is principle of wind power. So you have air entering or wind entering or and wind leading your wind turbine. Initially it will have some velocity, at the exit it will have some velocity. So across the wind turbine this wind will lose its velocity, okay, which gives rise to your axial force. So axial force is so this is cross sectional area. A is cross sectional area, okay. So this is your axial force on the wind turbine. Then from here you can calculate the power. Power generated. It will be rho A Vt by 2 Vi square minus Ve square. Vt is the velocity in within your turbine. So if initially it was V subscript I and after exit it's Ve in between within the turbine, what is the velocity? That can be value can be calculated. Okay. Through some mathematical operations that can be done and Vt will find out. Vt comes out to be basically Vi plus Ve by 2. Okay. Vt. But power here is rho A Vt by 2 Vi square minus V square. Alright. Then if you need to find out the optimum velocity for wind leaving, right? So you want to maximize your power. For maximizing power, what you do, you differentiate it with exit velocity and you say that it has to be zero. Okay, the concept of maxima and minima. At the maximum you'll have a tangent parallel to the x-axis. Okay, so when we do this, what we find out that v exit optimum is third of the entry velocity. So this is the optimum velocity. And here the P max, the maximum power that you generate is 8 by 27 rho A V I cube. Okay, but the total power that you have given to it is half of rho A V I cube. Okay, this is you have given, this is maximum that you can get from your wind turbine. In that case, the efficiency, if you find out what is the efficiency, maximum efficiency of wind turbine that you can attain is 0.593. This is the maximum efficiency that can be attained in a wind turbine. All right. So from your power, you can calculate torque by dividing it with torque is power by your angular velocity, right? The torque into your angular velocity is power. In rotational mechanics, if you see, like force into velocity is your power, right? The same way. So the expression for torque can be found out. Okay. And for axial force, we have seen. Okay, axial force we have seen. And in terms of diameter of the turbine, also we can calculate it. So this axial force and torque is done then. Now after this, we will jump to the questions. Question number 13. It says that in a wind turbine, the optimum velocity of wind exit is the product of inlet velocity and dash. Exit optimum, I've just told you, is bi by 3. That is bi into 1 by 3. So now if you see the options, C is the correct option. Okay. Question number 13. Next question, question number 14. It says that considering a wind turbine, which of the following is above the bed's limit? Now, what is bed's limit? Bed's limit is the maximum efficiency of your wind turbine, which is 0.593, or this. So, which of the following is above bed's limit? If you see three options, they are well below your bed's limit. You see fourth option. This fourth option is above the bed's limit. Okay, 64 is greater than 59.3. D option. So I forgot to change the value. 10 here, 1.23. So these are the values given to us. Speed, wind speed is given, density of wind is given. Then find the total power density available with wind stream. Total power density we need to find out. This is question number 15 solution. Total power density is power is half of rho A VIQ. The P total that we have talked about. Okay, PT, P subscript T, that initially is available with the air. Now they are asking for power density and its unit is watt per meter square. So, which means they are asking for what this? They are asking for this thing, power by area. Now, density we have 1.23 and velocity we have 10. Calculating this, the answer comes out to be 615 watt per meter square. So this is the answer to question number 15. Question number 16, it says that maximum power density obtainable from the wind stream is. Now maximum power obtainable is 0.593 of the P total. But if you want to find out through the formula, That also can be done. Emacs. So this is this. Okay. This was question number 16. I hope there is no doubt in this question. This was last question, I believe, of lecture number 27. Then we have lecture number 28. So in lecture number 27, we saw wind energy potential, right? How we get, then principle of wind power, how we get power from here. The potential wind has and how we get power from here, and the different forces in a wind turbine. So this we saw. Then lecture number 28. The topics are wind energy. Sorry. So the topics are wind energy potential, Magnus effect. Magnus effect basically is the lift generated. Then wind machines, horizontal axis wind turbine, vertical axis wind turbine. Then some designs and wind turbine operation. So this is your last lecture of this week's content and also of this session. So wind energy potential has been discussed in previous lecture. In lecture number 28, Magnus effect. What is Magnus effect? Let's say we have a cylinder, its cross section is like this. About this axis, it is symmetrical. Now, if some fluid is moving around it, So it will be like this, streamlines. Okay, these are your stagnation points. Here, the cylinder is not rotating, but what will happen if your cylinder start rotating? In that case, this is the axis. The stagnation point shift to here, and your steam lines go something like this. And the pressure profile change in such a way across the about the symmetry, right? So there is section above the symmetry, there is section below the symmetry. The above section is facing some pressure, experience some pressure. Lower region is also experiencing some pressure. Okay. When the cylinder was not rotating, the pressures on the upside and downside of this symmetry were balanced. So there was no net force, okay, perpendicular to this axis or perpendicular to the flow. But when the cylinder starts rotating, it gives rise to circulation, okay. And because of this circulation, there are velocity differences on the upper side and downside of your cylinder. Also, there are pressure differences on the upper side of your symmetry and downside, lower side. And this pressure difference gives rise to a net force, okay, which is lift. So this effect is known as Magnus effect. Okay. Then are your wind machines. So your wind turbines can be horizontal axis and your vertical axis. So if this is ground, this is your turbine, this is the axis. The turbine is like this, it is air is coming like this, going like this. So this axis is parallel to your ground. So this is horizontal axis wind turbine. If your axis is perpendicular, okay, if it is perpendicular to your ground, in that case it is VAWT. Okay. So this is basically VAWT and HAWT, and then comparisons have been drawn like VAWT is not suited for your heavy winds, okay, and efficiency of your HAWT is higher than VAWT. Also, one drawback of HAWT is that though it is efficient, but it is more noisy. So all this has been discussed under this topic. Then wind turbine operation has been discussed. So this has been briefly this has been discussed where two terms are important. One is your cut-in velocity, second is your cut-out velocity. So what are these? So cut-in velocity is the minimum velocity at which your wind turbine works. So your if the velocities are lower than cut-in velocity, there will be losses. Okay, the losses will be higher than what we have in our hand to produce electricity. So that is not recommended. That is why cut-in velocity is specified for a particular wind turbine, and your wind speed must be at least this velocity. Only then we run the wind turbine. And cutout velocity is the maximum velocity beyond which we don't want to go. Otherwise, this can damage the wind turbine as there will be loads on the wind turbine that it might not be able to withhold. So this was it about question number 28. Then I have one question from this lecture based on the statements given below, which is the correct option. The rotating cylinder in a uniform stream gives rise to lift. That is correct. Circulation is the effect of rotating cylinder in a uniform stream. That is also correct. So both the statements are true. One is false, second is false. No, both one and two are true. C option. So C option is the correct option. This was question number 17. And so we are done with today's session. Now I'll conclude the session. Four lectures were there, lecture 25 to 28. First two were on hydroelectric power plant. Next two were on wind energy. In first we saw hydroelectric power plant, its elements. Then we discussed Pelton turbine, its velocity diagram, and that it is a purely impulse type of turbine. Then other types of turbines were discussed in lecture number 26, like Francis turbine, propeller turbine, and special case of propeller turbine, Kaplan turbine. Okay, where blades somehow can be adjusted. Okay, then their velocity diagrams were discussed, and these are reaction type of turbines, right? And the direction of flow in Kaplan and propeller is axial, and in Francis it's radial at inlet, and at exit it's axial. Then after that, we moved on to wind energy, where we saw the potential the wind has, okay, in terms of the kinetic energy, and how we can harness it using wind turbines, and what are the forces like axial force and torque that your wind turbine experiences, expressions for it, and the optimum exit velocity we saw for maximum power that can be generated from a turbine. The maximum power that can be obtained from a turbine in terms of percentage is your BETS limit, which is 59.3%. Then in lecture number 28, we basically saw Magnus effect. So this Magnus effect is used in your wind turbines also. Okay. And then what are horizontal axis, the HWT and VWT, based on the axis of the shaft on which your wind turbine exists. Okay. So this was it about session number 10. And thanks for watching. And session number 11 will be on the same day, Tuesday, next week, from 6 to at the same timing from 6 to 8 p.m. Till then, goodbye and thank you.